Hello and welcome to Technological News.
Today's topic: Microdrones propelled by light-driven nanometers. A handheld laser pointer produces no noticeable recoil forces when it is fired, even though it emits a directed stream of light particles. The reason for this is simply because of its relatively enormous mass compared to the very tiny recoil impulses that the light particles cause when they leave the laser pointer. However, it has long been clear that optical recoil forces can indeed have a significant effect on correspondingly small particles. For example, the tails of comet points away from the Sun partly due to the light pressure. The propulsion of light spacecraft via light sails has also been discussed repeatedly, most recently in the connection with the Starshot project, in which a fleet of miniature spacecraft is to be sent to Alpha Centauri. In the journal Nature Nanotechnology, Worksworth's physicists led by Professor Bert Hedge, chairman of Experimental Physics 5, nano-optic growths, have now shown for the first time that it is possible to not only effectively propel micrometer-sized objects in an aqueous environment with light, but also control them precisely on a surface at all 3 degrees of freedom, 2 transitional and 1 rotational. Size comparison between quadcopters and microdrones by Xiaofei Wu. In doing so, they were inspired by ordinary quadcopter drones, where 4 independent motors allow complete control of the movements. Such control possibilities offer completely new options for the usually extremely difficult handling of a nano and micro objects. For example, the assembly of nanostructure for the analysis of surface with nanometer precision, or in the field of reproductive medicine, polymer discs with up to 4 light-driven nanomotors. The Worksworth microdrones consist of a transparent polymer disc measuring 2.5 micrometers in diameter, and up to 4 independently addressable nanomotors made of gold are embedded in this disc. These motors are based on optical antennas developed in Worksworth, that is, tiny metallic structures with dimension less than the wavelength of light, says Zhao Fei, a postdoc in the Hedge research group. These antennas were specifically optimized for receiving circularly polarized light. This allows the motors to receive the full light regardless of the orientation of the drone, which is crucial for applicability. In the further step, the received light energy is then emitted by the motor in a specific direction to generate optical recoil force, which depends on the sense of rotation of polarization, counterwise or counterclockwise, and on either end of 2 different wavelengths of light. It was only with this idea that the researchers were able to control their microdrones effectively and precisely. Due to the very small mass of the drones, extreme accelerations can be achieved. The development of the microdrones was challenging. It started back in 2016 with a research grant by the VW Foundation dedicated to risky projects. Precise fabrication based on single crystal gold, the extremely precise fabrications of the nanomotors is crucial for the function of the microdrones. The use of accelerated helium ions as a means to cut nanostructures from monocrystalline gold has turned out to be a game changer. In further steps, the drone body is produced using electron beam lithography. Finally, the drones must be detached from the substrate and brought into solution. In further experiments, a feedback loop is being implemented to automatically correct external influences on the microdrones to control them more precisely. Furthermore, the research team strives to complete the control option so that the height of the drones above the surface can also be controlled. And of course, another goal is to attach functional tools to the microdrones.